Okay, thank you very, very much. I think it's actually I'm very glad to meet you guys once again. Yeah, actually it's been a while. All right, so I don't really know. Have you guys read any resources concerning the shell project, or possibly we should begin from the whiteboarding? Then maybe we should just go straight to the implementation, the practical aspect. Yeah, so where should we start from actually? Yes. Oh, actually,
Probably start
it
from the
was a
very beginning, Genesis.
okay. So, all right. Hmm, it's going to be fine. Okay. So,
I would
if
suggest I would suggest if we can look at the concept page, begin from there.
okay. Yeah, I'm here. Don't worry, I'm here. I'm trying to open my whiteboard actually. Yeah, we're just going to do with some short implementation, like um, the parent and how those let me see how the simple shell itself it runs. Yeah. Then after that, if the need be that we implement it practically by coding, then we just go straight to that. Yeah. So basically, if you really could check how the shell works, um, there is something that is consistent about the shell. All right. It is always active. It is waiting for you to input something, right? Sure.
Yeah, we are with you. I'm with you.
So there is, yeah, so there is one particular, actually in C, we got to know that mostly when you want your program to stay active on the screen, you have to use what? The loops. So whether you prefer to use do while, or whether you prefer to use while loop or for loop or whatever, it depends on what you understand and what you want to use. All right. Yeah. So actually, that's all about the simple shell. So once you are able to tell your program to wait for the user to input something, then you take that input, then you execute or you do as the user instructs you to. You're already done implementing the what? The shell. And that's the same way that the shell also works. It accepts an input. Then it does it for you, just like every other program does. All right. Okay, so I think my whiteboard is done opening. Let me share that with us now. Okay. So this is our white screen. This is our board. So we are going to actually work on it. So let me just type in my title. So simple shop, right? Right. Boom. That's our heading. Now, let me take my pen. All right. If we could actually check the requirement, there are certain consistent functions that we can actually use. And throughout the weeks or the previous weeks after the print F project, you guys have learned about linked list, all right? Yeah. So double linked list and all that. so you know how to use all of this. So all these applications comes out based on your taste, whether you prefer to use a linked list or whether you prefer to use any other thing or any other data structure at all. So we are just going to deal with the basics. So we have a particular function that's ALS prefer we are supposed to use. And execv is actually a function, all right, a system function that actually it's actually a C standard library function. And one thing that it does is that it doesn't execute on its own, but it will just look for another program in a particular path, and it will call that program and it will execute it for you. So that's what the execv does. We have other classes of this particular function. We have the execpl, I think so. And we also have is it execv without the e, all right? And we have this one too. So I think we have almost about 5 or 4 variations, but each of them have arguments that they accept and what they do. But in ALX, they are actually advising us, and it's recommended that we use this particular function in our code. So if you use any other function apart from this, the checker will flag you because it is actually looking out for this particular function in your code. Right? And we also have to utilize the use of PIDs and also ppid. And definitely we know what PID means, is what is process ID. Right? And the ppid is actually parents process ID. Right? I think basically these are almost all the functions that we'll actually use. And for this particular project, you can actually use the inbuilt printf function, all right? You'll not be flagged, so you can actually use that. And I think, what again? Okay, so we also have another function, which is getLine, all right? So we use getLine to read an entire line, all right? So just like, maybe if I type, hello, good morning, all right? Evening, it's actually evening. All right. This entire line is going to be read by the getLine. So you see that the getLine works exactly as the scanf works, but getLine actually accepts a buffer, all right? Then it will also calculate the what? The size of the buffer. So let me put in size. All right. Then the last parameter is going to be, where do you want the function to read the input from? So is it that you want it to read the input from a particular program, or you want it to read it from the standard input? And we know that standard inputs actually signifies whatever input that the user will enter right from the keyboard. So stdin. So this actually means that every single input that is coming from the keyboard, we want to call this function to read that. So when that input is being accepted, it will calculate for the entire size of the buffer, and the buffer 2 is going to be the entire string. All right. Now, we can also actually utilize our arguments, which is our argv, all right? That's argument vector variables. We can actually utilize those. So you can actually use that. Yeah. So I think for now, this all that I recall, right? This all that I recall. Maybe along the line, if any other function pops up, then we'll implement it here. And definitely throughout this very program too, since we are using getLine actually uses malloc, all right, or possibly dynamically allocate a space for this particular buffer. So at the end of your program, you have to remember that you should free the buffer, right? So don't worry, we're fine. We'll actually get this. So this is just a reminder, all right? So in case if I forget, definitely I will recall. But in case if I forget, please, somebody should just remind me. All right. So for now, these are actually the functions that we are going to implement. Yeah, these are actually the functions that we are going to implement for now. All right. So actually, what is exec v? So as already explained.
I wanted to ask a quick question when you explained that get line. The size refers to the size of the buffer, right? The line that get line trying to read.
Yeah. Exactly.
Okay, is that how it dynamically allocates size for the line?
Please, I don't get what you mean. Please come over again.
You said the get line will allocate a space for the line, right? So I'm not saying that are we going to specify the size of the memory by the this stored argument in the get line function?
Okay. So actually, this is none of this is up to you. All right. Get line will automatically allocate all these things for you. So all that it needs is just for you to point where do you want it to read the input from. And you specify that we want to read it from the standard input. So get line, whenever that the user inputs something, like as the shell operates, there is always a prompt waiting for you to input something, possibly a command, just like ls, maybe cd, or any other command. All right. So if you input an instruction out there, getLine will automatically take that particular input, allocate or what a memory for that, or possibly a space for that. All right. So this space or the size of that particular input will be stored in this argument, or possibly this particular variable. So I think in the man page, they actually denoted n. All right. And it's actually of the type size t. And we all know what SS size t and size t they do. All right. So it's actually the size of what? Of the buffer. So just like in bytes. So if it is 2 characters, for example, it is actually going to allocate what? 2 bytes. We know that actually 2 characters, one character is just 1 byte. Right, so it's actually going to allocate 2 characters for that. And it's an unsigned long int, right? And we know that unsigned long int actually have a vast range when it comes to what? To allocation of what? Of let me say, when it comes to allocation of what? Characters. And the buffer is just like a character pointer. All right. So the buffer is a character pointer and it's actually going to store that string. I hope you understand that.
Yes, thank you. It's clear now.
Cool. All right. So that's what the get line does. And there's the specialty about get line. And the reason is that scanf works far different from what get line. And get line also works in a specialized way, because it allows you to be able to what? To manipulate the data that is accepted from the user. And yes, we also have other functions that we can also use. We have string talk, right? Yeah. So we use it to tokenize strings. So we can actually use this because once we accept an input from the user, we need to tokenize our string. That means that we need to split that string in separate words. That is the same way that an AI works. So if you understand this particular concept, I believe you, when you are good in Python, you can actually develop, let me say, an AI for it to work perfectly fine. All right. So if you understand tokenization, it's cool. So just like I typed hello, good morning, good evening, right? Right. So the string talk will actually use, or possibly will actually accept the token, all right, and it will also accept the delimiter. So let me just say token, all right, then the delimiter. So the delimiter actually means what's parameter, or possibly um, um, what signal do we want to pass to the command, or possibly the function, so that when, man, I've cleared it.
I think there's an undo button down there.
Yes. But I don't know. I think it is because I was using, let me say, I was using Grammarly. So accidentally, my hands typed on that, and Grammarly just cleared it for me. So that's the problem. So is it that actually, so we had the command, which is strtok, with the string talk. So it accepts the token, all right? Or possibly it will accept the buffer instead, right? Then it will also use the delimiter to split that buffer into separate words. So just like an AI can actually is your entire sentence and will actually detect names from verbs and also pronouns from any other let me say any other word. That's how the string talk also works. So it's just going to split your entire buffer into separate words. And the delimiter is actually what is it that should separate our what? Our words. All right. So that's what it actually means. So just I use hello, good evening, right? Yeah. So if we pass this particular buffer to our function, all right, which is string talk, is actually going to split this string into these different words, right? So you see that it's actually going to split them like this, all right? You see that whenever that's a particular function, let's just like the printf function, when it's reading through a string and it gets to the end of the string, we know that the last line should be what? Should be the end of, that's the new line character, right? Yeah, and the new line character will actually drop that cursor to what? To the next line. Yeah, so it's actually going to use that new line character to cut off these subsequent words. And actually, we are actually going to utilize these loops. So don't worry, when it comes to the implementation, we just get it. Let's just deal with the functions. So you also have string talk and what again? Yeah. So so you can also prefer to also use malloc, all right? Because there'll be more pointers. There'll be more pointers in what? In your code. So definitely you end up using malloc along the way. So definitely you also have to use free. All right. Okay. So now we are done talking about these commands, right? Which is a printf. We know what printf actually does. We know what getLine also does. And I've explained every single argument. Yeah. And the string talk to, I've also explained every single argument. We know that malloc, we use it to dynamically allocate a storage for a particular variable, right? And free, we also use it to what? To release that particular dynamically allocated memory or possibly space. Now, exec v, I think I explained it along the line. So exec v is actually a function, and it actually reads through your system path. All right. So you have to actually allow exec v to read through your path. You know that when you guys were when we're learning about a simple shell project, or possibly this, the basic shell, yes, the basic shell project, for example, we got to know that the Linux system actually uses what path, or possibly uses what an environmental variable. That's environmental variables, of which most of them I think we have path. We also have So I think the major one is what is the path. We also have the home. Yes. We also have the root and all that. So all these are what are also the major variables in the Linux shell, or possibly in the Linux system. So exec v will actually need access to this particular path. And in Linux, it is all caps, just like this. So this is actually an environmental variable. And this particular variable can actually expand and give you access to all directories or points you to installed processes or possibly installed programs in the system. That's the reason that you can actually type cd read or possibly cast the content of a file. All right. You can also actually use pwd, which is print my current working directory, all right, to actually print whatever that you have, where you are actually located in your shell. So you see that actually exec v is utilizing this particular environmental variable and is searching through those entire directory to see if the command that you passed is found in that directory or in those directory. So if it didn't find it out, it will just come and print it on the screen for you, that command not found. All right. So is it that actually my first time when I encountered the Linux shell, I was just trying to wonder, how is it that this program can actually tell me that this command does not exist? How does it do that? Until I gain much understanding about the environmental variables, that the path actually hosts all the directories to these programs. So when you call or possibly when you pass in the command, it will just search through this particular path and it will just search for them. If it is not there, it will just come and tell you, please, we don't have this particular program available. All right. So in hence what's command not found. And in the simple shell too, we also control D, which actually sends an exit status to the program to exit, all right, or possibly to close. All right. So oh, okay. Yeah, so where did I go off actually? Where did I go off? Yeah. Okay, so I was actually talking about the exec v command, right? Right. Okay, so actually,
Yes,
exec
you were.
v, yeah, all right, cool. So as I was already saying, the exec v is actually a function, all right, or possibly let me say a program, in C, which actually utilizes the path, all right, and if I if my memory actually serves me right, because I've not actually checked the man page currently, but actually it accepts two arguments, all right? And one is the path, and the other argument is actually the command that you want it to search for, all right? So execv will actually take that particular command, search through the path, and we know that the path is actually an environmental variable, one of the environmental variables. Okay, one of the environmental variables. So we know that the Linux system actually have so many environmental variables, of which I know that all of us, we are actually intelligent out here. We know most of them, all right? Yeah, we have the environmental variable that actually hosts the shell. So it's actually shell. Its name is actually shell, with all the cases being what? Uppercase. We also have the path, all right? The path, which is PATH, path. And we also have the home, right? We also have an environmental variable for the display. All those, they exist out there. So execv is actually just going to search for a particular command that you are passing to it. So since you are actually specifying that this is the variable that is hosting all our directory, or possibly all the directories that point to those particular programs, execv will just search through the environmental variable, which is the path, right? It will search through that particular variable and look through each and every single path. Actually, when we go to my shell, I'll actually print out the content of the path, and you see that it actually contains so many directories, and those directories are being separated, or they are being delimited by what? By a colon, right? So execv actually can actually utilize that, and it's a search through every single directory just for that particular single command. If that command was not found, it will just come back, all right, and just print it on the screen for you that command not found, all right. But there is also another aspect, all right. We have to also implement built-in commands. All right, we also have to implement built-in commands. So the same way that we are passing execv to look out for a particular command for us, we also have to implement a particular condition that will check and see if that particular command that we passed is not found in our path. Let's just search it through our built-in commands. If it is there, then we want to execute that particular command. I hope you get it. Yeah. So it's some way somehow similar to that of the printf the printf project that we just did. I think some weeks ago. You could see that you just pass a format specifier, all right, and you just look through. You can either use the switch cases or what for the printf, and it will just look through those individual cases that you passed, and it will see whether it matches. If it matches, it will just call that particular function to just do the printing for you. So that's the same thing. We just have to use condition to just look through our functions. And if that function is actually the same as what the user passed, then we just want to do that for him. And we need to implement, I think for ALS, we need to implement aliases. We need to implement the exit status, where you just press the shortcut key, which is the Control D, to exit from your program. And I think in the advanced task, some way, somehow, you need to implement where you type exit in your shell, and the compute of your program or your shell will actually respond by closing, all right? And we also need to implement the cd command, all right? The cd command actually allows you to change directory from one place to the other. That's from one directory to the other. So don't worry. I think I'm talking too much. Let's just box onto the whiteboard. So we also have the PID, and the ppid. So I think along for the first implementation, we'll deal with the PID, how it actually works, and what is actually the difference between the two, and how are they related. So we'll talk about all these for the implementation. And these are the first things, like the first thing that we'll actually talk of. All right. Okay. So the PID, as already said, is actually the process ID. All right. And PPID is actually parent process ID. That is actually their name. So if you see PID, it means process ID. If you see PPID, it actually means parent process ID. Now, what is a process ID and what is a parent process ID? Okay. Okay. So actually, you could see that every single program that you execute in your shell has its unique identifier. It's been assigned a unique code. All right. So that if you want to close that specific program, you can actually call its PID, or possibly specify its PID, or possibly its index. All right. We know that in arrays, we actually can utilize our items, or possibly our members in that array, by using the index of that particular array. And there is no way that a particular index will be holding multiple elements. Every single element have its unique ID. So that's the same thing, the PID. Every single program have its unique ID. It doesn't matter whether you run the same program at the same time, they still have their unique PID. It doesn't matter whether another program brought out another program, they still have their unique IDs. That's the reason that if you want to actually inculcate anonymity in your databases, for example, you can actually randomly generate codes for your users, and those codes are never going to be identical because they are randomly generated. All right. If that same if that same trend, or possibly that same algorithm, or possibly that same code could be the same, then actually I don't think it's going to be within that same time frame. It's going to be a very long time. All right. Like maybe some years ahead before that same code will be regenerated again. So PIDs are actually automatically generated by the system, and it is unique, specifically allocated for that particular program. And it changes on every single running. So when you respawn the program, the PID is actually going to change. So with time, it's not going to be the same PID, but it's going to change intermittently. All right. Okay. Now, so actually they are all the same, right? But there is a slight difference. The parent process ID is just like a mother and a child, or let's take it like a parent and a child. All right. So the only way that a particular program can have a parent process ID is when it has a child process. Please, do we get it? Or I need to explain further. All right. So let's take it this way. Let me see if I can implement it.
Repeat that statement you made.
Okay, so what I'm saying is that the only way that a particular program, all right, can host a parent process ID is when it has a child process. All right. So actually, don't be confused about the child process. So since it is a parent process, when that program brings up another program, that next program, or possibly that new program, is going to be a child process. So for example, let's take it like our Slack that we are hosting this session right now. All right. Slack is the whole entire program, all right, that we are running. All right. But within Slack, there is a huddle going on. And if you are actually acquainted, or possibly if you have some experience in what is let me say in web development, you will be able to know that actually when it comes to or possibly let me just say mobile development, all right, yeah, or possible application development, you'll be able to see that actually when it comes to an entire view of an application, every single section, we can call it what? A separate component. All right. So you can say that when you take this particular section, its view is unique. All right. It doesn't affect the other. That's the reason that every single channel does not conflict with the other. You can send an information to a particular channel and it doesn't. So Slack is the entire program. And within Slack, we have these various channels out there. And currently, we are hosting our huddle in core 16 channel. And I know that in core 18, they are also hosting their session also there. They're also having a huddle out there. But there is no conflict. And for me, I'm not experiencing Slack, all right? Yeah. But if you really go back and if you really check the processes that are running in Slack, you'll be able to detect and know that they have their unique process IDs. All right. Their unique process IDs. And these handles are child processes of the parent process Slack. Do you understand that? So in our shell, the entire shell itself, the main program, is going to be a parent process if it brings a new program on board, just like if you call VI out of your shell, right? VI will become a child process. And the shell is the parent process because the shell is hosting VI, which is a child process. And we also know that you can open multiple shells over and over again. And since they are being spawned out from an old or possibly an earlier shell, that shell is a parent process. And the subsequent shells that you are opening, they are child processes. All right. You will get this in deep detail when we go to our shell. Okay. So any question for this for now? Because I think we are almost done explaining all this. So first of all, we just talk about the PID and the PPID. All right. Okay. Any questions so far? So that we just move out from here, then we just go to just explain the practical explanation how the PID works and the PPID they also work. All right. Any question, please? Please, did I explain it very clearly? Or possibly I was moving faster, or maybe there are certain words that I used that didn't explain everything very well. Please, any question, or we should move on?
No, please, we can move on.
Okay, thank you. All right, so if that is the case, then we are going to our shell, right? Okay. All right. So our shell, where are you? Okay, so our shell is now on board. Please, I believe you guys can see it clearly, right? Cool.
Yes.
Wonderful. All right, so now we are just going to implement PID, just to get how it actually works. All right. Now let me just VI, then PID. Let's see. And just make it small. So okay, it's PID.c. Okay. But before that, let's use the man page. Right. So actually, the function itself is not called PID. All right. It is called get PID. We use that to what? To read the let me say the identification number, or possibly to assign that unique number to what, to that particular program. So we have get PID, and we also have get ppid. All right. So that's what we are actually going to use out here. If you read the man page, you actually see that we have get PID, get ppid, and see get process identification. So we use this program to actually get or possibly read the special identification number of our programs. And we know that PID actually comes from where? The unistd.h. Cool. So that's where it comes from. And it actually utilizes this particular data type, right? PID underscore T. Right? So if we create our variable, we have to make sure that we initialize, or possibly we declare our variables with this PID. All right. Okay. So any question concerning this? Okay, so let's read this to the description. So PID returns the process ID of the calling process. So this is often used by routines that generate unique temporary file names. All right. Okay. Now, the get ppid returns the process ID of the parent of the calling process. So do you get it now? So get ppid is actually it allows us to read the process ID of the parent process, and this actually utilizes at each usually goes with the child process. All right, and it's actually temporary because with time you end up closing the child process when you don't need it. Just like the header, when we are done with the header, we will not keep the header hanging. We just close it or end it. All right, cool. Think as it. Okay. Now, yes. So ALS will also let us use fork. Cool. So fork also allows you to be able to spawn a child process out from from a parent process, that the child process will be dependent on the parent process. All right. So just like, as I already said, that the parent process will be hosting the child process. So fork allows us to be able to do that. Let me open the man page for fork. All right. Whilst we just, so see, fork creates a child process. So fork allows us to host the child process on the parent process. Cool. All right. So fork creates a new process by duplicating the calling process. The new process is referred to as the child process. The calling process is referred to as the parent process. All right. Any question with the PID, the PPID, and the fork? Okay. Now, fork 2 comes from unistd.h. All right. Now, let's go to our application. Hash. Okay. Now, we need to include uni. That's io.h. Yeah, because we'll be printing something out, and we need to also include std, and let's add our main header file. And we are not going to accept any arguments. It's going to be void. And we know that we need to use PID underscore T to initialize our variable, or possibly to declare our variable. So PID underscore T, and we say PID, right? Now we just want to read PID for now. So we just say, PID is equal to get PID, right? It doesn't accept any argument. It's just like a function, a complete program on its own. So let me use a comment to explain that. All right. Then let's just say printf %D. Sorry about that. We need to add our return statements. Then we are done. We are just dealing with the PID for now. Then we also utilize the ppid. Then along the line, we'll try and utilize fork, include fork. So we'll see how fork actually also works. So let me exit. Please, any question with the implementation before? Okay, so we just declared, declared our variable. We assigned get PID. So get PID will read the identification number of the process and it will assign it to PID. Then after that, we'll print that identification number out on our screen. So that's what we actually do. Oh, I didn't actually end my comments. Let me close my comment section. All right. So GCC, PID and us. Okay, now it worked. Now see, we have 1556. Let's rerun it again. Now see, it has changed. So you see that it is temporary. It is not consistent. If I rerun it again, see, it is changing with time. Same thing, it is also changing again, right? So, as I already said, it's randomly generates what? A special identification number for our codes. For example, if I type PS and I add AUX, right? I think this here. So you can see that these are all the processes that are running on my virtual system, right? I don't have much running out here. So you can see that these are all the processors running on my virtual system. And you see, there's the command, there's the time that it was being started, all right? Like, okay, it was started this particular time. And yeah, so this actually how long it was what it has kept running. Yeah, so this is actually 53 minutes. Yes, 53 minutes. That's MySQLD. So it's actually let me see, MySQL. That's my SQL database server. So it's actually running, and it has run for 53 minutes. Okay, so that's just by the way. If we come here, we can see PID, all right? And see the first process that ran when my system started, it was an init command. And see, it has been assigned a PID of 1. All right. The next process 2 is what's plan 9. And I don't know what that actually does. And it's also been assigned what? A PID of 4. The same thing too, there was also another init program that was started. But you see that the stats are actually different. This one is SL, this one is S. So they are actually different stats. All right. And it's been assigned a PID of 12. So you see that actually, if they were having the same PID, if I decide I actually want to close this particular program, automatically my terminal, or let me say my shell, will shut down because they are all having the same process ID. But since they have unique process IDs, if I decide, hey, I just want to close this particular program, if I just close it right now, this one will still be hanging. It will still be running. So is it that it is not dependent on any other program because it can close on its own because it's hosting its own PID. All right. And we could see that this program, bin, right? I don't know where. So there's also actually an SH shell and it's running MySQL in actually this particular file bin, right? And it's actually having a process ID of 447. So you can see that all our process IDs are actually unique, right? They are actually unique. Cool. So let's go back. Please, any question with the PID before we add the PPID to? Yeah. So actually, you see that my virtual system is actually not robust. All right. It is not a full system on its own. So most of the applications are limited. All right. Just like in other words, or possibly unlike actually install a full Linux system. That's a full Linux system on your machine or possibly on your laptop. All right. It actually it will be hosting so many applications. So that means that if your PID is going to change, it's not going to change by one because there are many processes that will be respawning, some will be closing, and others. But is it that mine is actually limited? All right. If I type just only the processes, all right? I type only just the processes. So PS, for example, you see that I'm just having bash and the new process that I just run, which is PS. So you see that the only process running on my system right now is actually bash. All right. Do you get it now? And it's having a process ID of what? 692. Okay. It's having a process ID of 692. And the PS is having a process ID of 1582. Let me try and do PS-L. So you see that it is now showing me more detail about my processes now. Now PS-A. Now I'm saying that I want to see all my processes. I see that it's still showing me the current process. So for me, my current shell or my current system that I'm running, which is my virtual system, is actually having limited applications or possibly limited processes. So if I rerun my program over and over again, the difference is actually not going to be vast. It's not going to be very huge. Actually, just as we can see from earlier here, the changes was just 4. All right, 1, okay, 3. Yeah, 1, 4, then it jumped to 12. So it wasn't that much huge. Okay, yeah. And the reason that I will actually confirm that the reason why it's actually changing by 1 is because there are no sub processes that are being spawned by the process that we run, by our program that we run, which is the a.out. There are no further process that was being respawned. All right. So you see that if I rerun it again, there is no other child process that ran out of this. So it's still going to change by 1. All right. If I type PS-A right now, you see that this one also increased by 1. Do you understand it now? Yeah. Please, is it answered? Okay. So we also have a particular command out here. We call it kill or, all right. And you see that they've specified a particular parameter out here, which we can use the PID to close a program. All right. So that's one unique thing about this. The PID allows you to close that specific program. All right. So it's very, very important. That's the reason. Even on Windows, we have PIDs out there. Even on Mac, it uses PID. So it's not only in Linux. All right. Yeah. Even in databases, we still have those unique identification numbers. If you have your identification card, you are being assigned a unique code that is for you alone. Right? Yeah. Okay. So let's go back to our file PID, and that's .c, and we are actually calling ppid also. So ppid is equal to get ppid, right? And for this one, I would say process ID is, then we just print it out. Then print f parent process ID s. All right. Then ppid, right? We just want to print the parent ID and the ppid out. And you see that there'll be some difference, right? So let me compile PID.c. Okay, it worked. Now see, our parent process ID is 692. Our process ID, which is the PID, is actually 1616. Let's rerun it again. Now see, our parent process ID is actually the same, but the child process ID, or possibly which is the process ID, is actually changing with time. So as when we read the man page, we could actually see that the parent process ID is what actually puts the child process. All right. The reason is because the ppid is actually a mother, or possibly let me say a parent, and there are multiple child processes that will be spawning out from it. You understand that? Just like our shell that we have here. Our shell that we have here, right? Our shell, if it has a PID, which is actually a process ID, that means that it is not going to be consistent, it's going to change with time. But we should make sure that we want to actually assign it a permanent ID. But a permanent ID does not mean that when you close this program and you reopen it again, it's not going to change. Right? So the reason that you need to assign PIDs to child processes is that they are actually going to be, let me see, they are actually going to be temporary programs, just like the cat command, which is the C80 command. All right. When you run it right now, it's actually going to be temporary. It's just going to cast the content of a file on the screen, then to just exit. So it's going to be assigned a temporary PID. All right. By a program that is going to run for maybe 2 minutes whilst you're going to do something in it, just like VI or any other thing, it should be assigned a parent's process ID, because you will need to close it on your own. All right. Yeah. So that's actually the difference between the parent processor ID and the PID. It's just that you'll be able to what, to respawn other processes out of another. That's why VI, you can actually open your shell inside VI. You can actually open another file inside VI. All right. Yeah. Multiple things that you can do inside VI. So all those things will be assigned child process IDs or possibly the PIDs because they are going to be temporary and they're not going to be permanent. I hope you understand that. All right. Now, so let's try and let's see if we can actually inculcate fork out here. All right. If we can actually inculcate fork out here. So we are just actually going to use conditional statements and we want to actually see, all right, if our program is actually going to run perfectly fine for us. So let me open, please, any question with the PID and the PPID before I move further again. We move further again. Is any question? Any question, please? All right. Yeah, I think I've not I've not paid attention to that. Please sorry about that. Okay. Oh, all right, cool. All right. So actually, PID and the PPID, these are actually out of our hand, right? Yeah, they are not things that we can actually deal with. Actually, these are system that's like it's being dealt with actually by the system itself. Right. So the system automatically does all these things. All right. Yeah. So we don't have any hand in that. Please, I believe you understand me. Yeah, we don't have any hand in that. Okay. So oh, please hold on. My laptop is running down. Let me put it on charge. Give me a minute. Yeah, I'm just plugging in my charger. Okay. All right. So we are opening our file. Okay. Okay, let's just try and update that. So PID. Okay, so we are just trying to continue. So here we printed. Hello? Yeah. All right. Oh, okay. You, you don't know about that. Yeah, we can actually open a shell from inside VI. All right, a terminal from inside VI. So, example, Vim. All right. Yeah. So I can just type temp and see I have my terminal up here. Whilst I also have my VI at the bottom here. And I can actually do ls to view the content of my file in there. I can actually also execute the program out there. Once I type exit, that's closed. Hope you get it. Yeah.
Sorry, please do that again.
I should go back again.
Yes, thank you.
Okay. So, okay. So, yeah, I was going fast. Okay. So, actually, Justice asked, what do I mean by shell inside VI? So, opening shell inside VI. And VI have so many features or possibly so many capabilities, right? So, you can actually split your screen into multiple views, right? So, one way is that you can actually split your VI into two. You can have your terminal whether at the bottom or possibly at the top. All right. So all that you need to do is just enter term in your command section. When you press enter, it will open a terminal for you. So instead of moving back and forth from your VI to save your file and run or possibly execute your code, you can just try and just do your code out here. And if you just want to test your code, if it works, you can just execute at the top here. Instead that it's running inside VI. You understand that? It's running inside VI. So let me try and close VI and let's see something. So you see that it is still VI because terminal is still at the bottom. So if I type exit right now, that's when you see that the entire VI itself closed. So you see that the terminal was dependent on VI. Do you get it? Yeah. So we opened terminal inside VI and it is dependent on VI because even when I close my view itself, which is my VI itself, sorry. Then when I closed my VI itself, it was still active because I was still having this prompt here telling me that I have my terminal open. All right. And this actually the view of VI. So if I just enter exit from here, you see that now it closed from that view and it came back to my original shell. And that's the same thing. You can respawn multiple programs or possibly multiple shells in your shell. Just like I can type sh, which is another variation of a shell. So you can type sh and you see that's another instance of a shell has been opened. And I can type ls and you see that it's working. I can also do cd, all right? There may be dots, all right? And it's actually also working, all right? I can also say pwd and it's working. And I can decide, let me try and open another instance again. So I'll type bash, and bash2 also is also another variation of a shell. So bash will open this. This doesn't mean that the previous shell have closed. This is another instance of a shell, and it's dependent on the previous sh shell that I opened. So if I type ls, it's still working. I can also decide to open another instance of sh, and it's opened again. I'll type pwd, it's still working. Now, let's see the number of times I'm going to type exit before it will close from my current terminal. So if I type exit, this is 1. See, it dropped back to the previous bash shell. if I type exit again, under normal circumstance, if you type exit in your shell, we know that it's supposed to close your shell and exit from the entire terminal. But see, it's going to take me back to the parent process, which was the sh shell. Now, if I type exit again, it's going to take me back to the parent process of the previous what sh shell. You see that it's just like great grandparents and whatever, right? So actually, that's how it is, just like a family tree. Okay, so I can also type another exit again, and now you see that that was the last instant, and it's closed my terminal, which you guys are not seeing the view again. Do you see it now? Cool. All right. So let me open my terminal back. Okay, so I think Justice asked that without saving and exiting, can you execute concurrently? Okay, can you reframe the question? I don't really understand. Is it that saving inside VI that you want to actually mean? Is it VI that you want us to save before exiting? Yeah. So just to try and clarify your question, because I don't understand that. So help me understand your question so that I'll be able to. Yes.
Okay. You did you opened the terminal within the VI editor. Now I was asking, probably maybe you are running some codes and you just want to, because before now we are used to save, quit, go back to the terminal, run the code, and then return back if you have errors and things like that. So my question now is, if you have terminal open inside VI, can you just save, then run the command within that same place while still looking at your code and getting the error message if there is any?
Yes, actually, yeah, I get it. So actually, you see that just like you're using Microsoft Word, all right? And if you input a new text in your document, for it to reflect in your folder that you've actually made changes to the file, you need to save, because if coincidentally there is a cut off of electricity to your system, you will see that the only thing that you will get is a recovery file, which is a temporary file that was being backed up because your system shut down unexpectedly. So that's the same thing for your VI. If you want to actually compile your code in the terminal or the instance of terminal that you open inside VI, if you want to compile that code, then you will need to save your file. That doesn't mean that you need to exit, but you need to save your file. And once you save your file, you can let me say compile it in your terminal and can run it right there without exiting. And there is so many ways that you can actually open VI without exiting. All right. So just like if I open VI, okay, I think I'm not in that particular directory. So example and shell. All right. So yeah, now. So VI PID. Okay. Now imagine right. So let's imagine this. I can actually decide that, hey, I don't want to exit from VI, but I've made some changes to my code. All right, so maybe this one, I've taken out the S and I've saved my file. I'm not exiting. All right. You can, in other ways, suspend your program. That doesn't mean that you are closing it, but you can actually suspend it by pressing Control Z and C, I suspended it. So you see that they've written here stopped. So it's Control, you hold Control, then you press Z on your keyboard, which is Z, the one that we know. All right. Yeah. So I can actually decide this is C, right? And I'll compile my code, I'll run it, and it is working. I can rerun it again, right? And it's also working. If I want to go back to my VI, I'll just type FG, which means foreground, all right? And we are back to our VI. If you also prefer, let me make changes to this one and let me remove the it's from here too. And let me try and, okay, I think for this one, for example, since there's another variation of VI that I'm using, it's impossible for me to respawn a terminal in this. So you see that it actually opened a terminal by chairman, and the view is something else, which is not really encouraging. All right. So actually, if I go back to Vim, so let me just type exit. Yeah. All right. So it's exited. Right. So let me go back to Vim instead. So I think Vim is much more specialized. So if I use Vim, right, you see that we opened it. If I hold Control Z, now it has been suspended. I can compile the code PID.C, and it's compiled all right. I can run my file, and it worked. And run it how many times I prefer, or possibly it doesn't matter the number of times that I run it, it will still run. If I want to resume back to my code or to my text editor, I just have to type FG, then I'll press enter. It will take me to what? To my code. All right. Now, we can actually also spawn another terminal inside there. And maybe if we make some changes in our code, and we want it to reflect out there, I'll need to first of all save my file so that it will reflect in what? In the shell. Because just like I use the Word document as an example, if you don't save it, those changes are actually not going to reflect. So even if you compile your code, it's actually going to be the same output that you're going to get. So for the changes that you made to reflect, you need to save it. Then once I'm done, I'll just come here, GCC, PID.C, I run my code and see that we have S here. But earlier on, I took out the S, right? So PID is 1741. And I can run it multiple times. If I want to exit, I'll just have to type exit, and we are back to RVI. All right, cool. Please, Justice, I believe it's answered.
Very much clear. Thank you very much.
All right, cool. So, we wanted to implement the fork, right? Okay. We wanted to implement the fork. Now, we are going to implement it in more detail. Cool. All right. So, actually, the fork command would end up returning a particular integer, right? A particular integer. So I think if it returns, let me see. Yeah, if it returns 0, then that means that it's actually still the child process running. All right. If it actually spawns another child process, or possibly if a new child process runs, they'll know that, oh, actually, the old process is actually now the parent process, and it's opened up a new child process. You'll see that there will be a new respondent of that. Don't worry, we are going to be fine. So let me just implement our conditional statements here. So it just actually returns either 0 or possibly greater than 0. And if it is not greater than 0, then that means that our forking actually fails. So it's either 0 or more. Yeah. Okay. So I'll just raise up the condition. But before that, we'll need to call the fork command. And fork also we utilize. Okay. So let's raise a variable. I'll just say C underscore PID. All right. Just to denote the child process. All right. So we know that as we read from the man page, that the fork command is used to spawn a child process or possibly to start a child process. So we can actually use fork to start a child process. The whatever value that fork will return, we want to assign that value to this. Right? Okay. So we just say C underscore PID, right? It's equal to fork. And actually, fork is not going to accept any arguments. Don't worry. Fork is not going to accept any arguments. So it just works the same way, just as get PID and get PPID and all that. Okay, so we just raise a condition and we'll see if C underscore PID is equal to 0, right? So if it's equal to 0, we want to actually say that this is the child process, all right? Then we want to print the parent process ID, and we want to also print the current process ID, which will actually be the child process ID. So just call print F, right? Yeah, print F. I would say child process. So let me just put in our definite article. So this is the child process. Right. Let's add a new line character. And we'll call our printf function again. And we'll use this to print the parent process ID. So let me use ppid so that I think we'll get there very well. So since it's an integer that will print out, we just have to use %d. Then we'll call in our PID, right? Yeah. Okay, so actually this is going to be an instance, like a new respawning of what? Because when fork runs, it's going to respawn a new instance. So we just want to call the get PID as we are running the loops or the conditional statements, so that we'll get those individual or possibly that particular PID. All right, cool. So just say there's the parent process ID. So get PP, right? All right. So it's just going to return that particular number to this, and it's going to print it out for us. Then I think, okay, yeah. So the next one, we want to print a current, or let me just put into bracket child. Says, which in our case is PID. Semicolon. This is column. Then I'll put my %d out there. New line character there. Then gets PID. Right. Okay. Okay, let's raise our else condition. So else if, yes. So else if C underscore PID. So in case if whatever that fork will assign or will return and assign to C underscore PID, if it is greater than 0, we want to actually specify that, hey, man, what is your problem? So, so we want to actually specify that this was actually what's being responded by the parent process ID. All right. So we see that you have the child process ID and we also have the parent process ID. And this next condition would be when the parent process ID started a new child process. All right. All right. Let me see if, and please, is there any question on the thread? In the thread, sorry. Okay, all right. Okay, so yeah, okay, so print F. Event process. Okay. And the next one. Child process ID. Okay. I get it now. So fork is actually going to, yeah. So fork will return the child ID, sorry. So let me put in C underscore PID. So I will get that child ID. I will print it out. So this is actually going to be the current process ID instead of the child ID. It's actually going to be the current process ID. Right. Okay. Let me put in the PID, but it's still the same. And I said here PPID, but it's not actually right. Okay. And I believe that's all. Okay. So what if our condition failed? Because I need to add the last else condition. So else, we just want to, I'm not going by. Okay. So these people, I just want to continue. So I'll just say print F. So if any other value at all, apart from 0 or anything greater than that, we just want to say that it failed. Then we just say return. Yeah, cool. Let's try and please, let's go back. Maybe any question? Any question? So here, this is actually the first implementation that we dealt with, all right? And here we want to actually incorporate the fork. And we know that fork actually allows us to start a child process. And as we already read, fork will return the special identification number of the child process. That's why we assigned C underscore PID. So this particular number will be the number of the child process. So if if it returns 0, that means that there is no child process that was being started. All right. But if that particular number is actually greater than 0, then that means that there is actually a child process. Okay. Yeah. And we want to actually print out that child process out on the screen. So that's what we're actually doing. Yeah. So we are just actually raising a condition concerning that. Cool. All right. So please, is it clear? Is it clear? Is it clear, please? Cool. So let's save our file then. ECC as usual. Oh, I forgot to add a semicolon. Man. All right. Now it worked. Now let's see something. Okay, I didn't implement more new line characters, so we are getting multiple things. So we get to know that there's actually the earlier instances that we dealt with. All right. So there's actually out there. Now this is a parent process. Okay. And we got the chance to print the child process, which is 1809. And we said this is a child process. Okay. And we printed the parent process ID, which is 1673, and the current process ID, which is 1809. Yeah. So the current process ID is actually the same as a child process ID, but that is actually not the case. All right. The reason is because our fork is running. All right. And for the very first run, fork will actually pass in the process ID does. The child process ID to our C_PID or whatever. All right. Yeah. But the first condition, let's go back and let's just check the condition. Let me make sure that everything is working fine. So here we say that this is the child process, okay, and yeah, this is the child process. This is a parent process. Okay. So this is a parent process. This is a child process ID, and we got 1809. So we got to know that actually there is, I don't know whether there is a jump somewhere, but we could see that our code skipped. That means that there was an instance where fork actually didn't return 0, right? It actually returned this to us. Like it's respond on the child process, and it returned this and said this is the parent process, the first instance, and we got the child process ID, right? And I don't know how it rerun it rerun itself again, but you see that it came back to the previous if condition, and it said this is the child process. It printed the parent process ID, and it didn't start any new child process. So we got the current process ID, right? So that means that our fork is actually working. It's not bad, all right? So the second condition was being raised, or possibly, yeah, the second condition was being raised, or it was true. So we got, this is a parent process ID, and that was when the child process ID auto started. So we now got the PID of the child process. And after that, that first condition, which fork will not start a new instance for our code. It's rather read, this is what? A child process. Okay. So let me try and put a clear gap between this. So I'll implement another new line character. Right. And all right. So I think this solve that. And let me try and add this one to then printf. All right. So let's save our file. Let's recompile. And it worked. Okay. Let's see. There's a parent process ID. Okay, we got 1858 for the child process ID. And this is a child process. And we could read that this is what the parent process ID, which was 1673. And the current process is what? 1858. You see that the child process actually returned its actual value. The second condition, which was being raised, this was when no other process was being respawned, like no other child process was being started. So you see that our process ID actually returned the same number as our child process ID, because the child process ID didn't start any new process. So let's try and inculcate if in case, right? I don't know how to put it, but okay, I don't want to make the code complicated because I wanted to actually raise a like call another fork command, right? So that we'll actually know if the fork is being called inside a child process, how does it also work? All right. Yeah, but I think our line of code is becoming too much. Okay, so that's actually how the PID and the PPID they work. All right, it just grants you the privilege to what? To yeah, hello.
Yeah, man. Yeah, sorry, I just wanted to get something. Right, you said the fork returned 0, right? Can you hear me? Man.
Actually here.
Okay, so
Can you hear
said
me? Yeah,
yeah, I can hear you now. You said the fork.
hello, Melvin. I think Tommy was Tommy.
Yeah, I can't see your screen. I think you gone off. But you said, according to your explanation, you said fork normally like returns 0 when it's a child process, right? Or parent. Am I
okay? So fork will actually return the PID of the child process, because when we read the man page, fork is used to start a child process.
Okay.
All right. So when they start that child process, it will automatically allocate that PID to the child process. So if fork returns 0, then that means that the child process never starts, like it didn't start.
It didn't start.
Right. If it returns any number at all, apart from 0, or possibly if it is not greater than 0, or if that particular number 2 is also not equal to 0. That means that if it is negative, then that means that
It's
the
negative.
fork failed. It failed
Fork
to
failed.
like run. Yeah. So
Okay.
that's what we're just trying to.
Okay, so from this first condition, which we say if child process equals to 0, we are saying that
Yeah.
the child process, okay, and the parent process
Yeah.
ID, which it returns, right? So
Yes. So
and the else, yeah, go on.
so yeah, you were talking, so I was actually listening. Don't worry.
Okay, so which that first condition, which says the child process if it's equals to 0, then this statement the print the process ID, which is the parent, and also the current ID, which is the child process, right? And the other condition, which is the else if the child process ID is greater than 0, so which it could be 1, 2, and above, they should return they should print out the parent process and the child process. And lastly, you said else. So any other number that's basically is the negative number is returning. My question now is, so for instance, in this case, what if we call another for function in the else if statement, in the else if condition?
Yeah. So that's yeah. So that's what I actually wanted to implement. Right. So that we would actually check how it actually works. You see that in your program, you're not going to implement multiple forks for every single program. Right. The simple shell project works with a loop. Okay. So if a program is being spawned or possibly is being started, it will automatically call the fork command. All right. So that it will be assigned the PID. Do you understand that? Yes.
Yeah.
So that's how it is. So it's not that every single program is going to be assigned its own fork command. No, the fork command is just for the subsequent child processes. Yeah, so that's why I'm actually very afraid to inculcate the fork command a second time in our conditional statements, because that won't be part of the implementation when you're dealing with the simple shell projects. The fork command will be called only once.
Okay.
All right. Yeah. Because
Okay.
actually it cannot happen that there will be multiple forks running at the same time. All right. I don't know how to actually explain that for you to get it. But I see that every single program opens at a particular time and it's been assigned its unique identification number. As I already said, that even if there is a twin program that was being started, they will still have their unique identification numbers. All right.
Okay.
Yeah.
Okay.
So yes, we can actually decide to call fork again. All right. So let me try.
So my issue, like what I want to know is that the implementation of that. For instance, if we call, I'm just saying, like, for instance, if we call another fork within the else, the if else, so the else statement, right? If we call another one there, from this point already, we had the parent process, right? And we have the child. Does it have to be like this time around, the child process will now be the parent process for this? That's what I want to know. Do you understand what I'm saying?
Come over again. Yeah. Okay.
So if we call another for function here, does that mean, because here we already have a child process, right? in the else statement.
Yeah.
I don't know if you understand. We have yes, good. We have that. So I'm saying if we call another for process or function there, does that mean that the child now will become the parent for this statement, or how would I call it, like a for
Exactly.
this statement
Exactly.
or this
So it's,
process?
yes. So you see that actually, as I already was explaining, that it works just like a family tree. Okay. So you have the parent at the top, and the parent will give birth to the child. The child too can also give birth to another child. And now you will be what? The grandparent. Okay.
Okay.
And if the grandchild give birth to another child, you will be the great great grandparent. You understand? Or but yeah, the great grandparents. All right. Yeah, so that's how it is. So if you just want to come to the top, you see that the child is the child, but the okay, let me go back to our terminal and let me try and use it here. So we have yeah, hello. Yes. All right. So okay, so no problem. So let's just move on. So let me just try and clarify this, then we just box onto that. So just like we have P1, all right, and we also have P2, all right, we have P3. Then this will be what? C. So you see that this is actually the child, and this will be what? The great grandparent, all right? And this is actually the parent. This actually the grandparent. Do you get it? So this is currently the current process which is running, and it is dependent on this, the parent. And for our case, or possibly in context of our program that is running, this is still a child process of this parent process. All right. Please don't be confused about the parent and the child. All right. It's just like a simple visualization that you can actually use for that. So there's the child, there's the parent. So if this is a parent and it is dependent on another program or another process, then definitely that means that it is also a child of that particular parent. The same way that this is also a child of this parent. Do you get it now? Yeah. So you can actually respond processes dependent on each other. Just like when we use the SH and the bash shell, and we opened it multiple times, and we actually closed it using the exit command multiple times before it finally got to the last parent, or possibly the last process, where when we entered the exit, it closed the entire program. All right. Okay.
Thank you. It's clear.
Now, the final thing, then I think because of time, so we'll be yeah. Yeah, don't worry. So now, I think for now, we are done with the PID. And for the exec V, we actually need to get there before we can actually decide to utilize the exec V. All right. So maybe we'll just start with a simple implementation of how the simple shell works. All right. Then how it actually accepts an input. How we can actually use the shortcut D, which is the control D, to actually exit from the program. Then maybe, I don't know whether we can meet tomorrow or possibly on Wednesday, then we can actually implement the other function, which is the exit v, where you can actually use it to what? To pass in that subsequent command and look through the path and retrieve that particular command for us. So first of all, when it comes to developing a project, we know that since it's C, we have some basic files that we need to actually implement, which is our header file, right? Main.h. Then maybe we also have our main.c, because for this, we are not dealing with the function, but we are dealing with a real program itself. So you can decide to name it main.c, or you can decide to name it shell.c. Actually, ALS doesn't specify that you have to name your file this way. Okay, so I think for now, we can actually utilize this. And we can decide that, hey, let's just implement our prompts also here, all right? Don't worry. Anyways, we'll know what this means with time. So let's go to our main.h file. I forgot to use my VI. And since it's a header file, we need to define the boundaries. So all right, let's include our C libraries, the ones that we'll be using for now. So first of all, the constant one that we know, we've been given the privilege to use printf. So we have to include our stdio.h, right? And so for now, let's just use this. So go back to our main.c file, right? And we include our header file out here. Now, then all right. I believe you can see this comment section very well, but it's very faint. Okay. So this our function. It's actually a main function, all right? So for now, let's just say void. So you are not going to accept any arguments. So first of all, we know that when you are implementing, like when you run your shell, or possibly when your program starts, it actually prints something on the screen. Like there is some text, or let me say there is an indicator that you see on your screen. All right. So that particular indicator, it's actually being denoted by either the $sign or maybe how specially you want to denote your shell with. All right. Just like when we started the SH shell, we saw only the $sign. But if I move back to my bash shell, you will see my username, you will see my system's name, you will see my directory. All right. That's my root path and all that. Yeah. So currently just have to define our prompt. And our prompt is going to be multiple characters. So we know that we have to incorporate what? A character pointer. And let's just name it prompt. Right? Cool. And how do we want to name our shell? What do you want to see on the screen? Let's just say into brackets shell. Then let's add our dollar sign. I remember that you need to leave a space between the last indicator and your closing quotes so that there will be enough space for the user to input something, right? So that's why I've left this space here, right? So now I'll just call my printf function, then send s, since it is what? It is a character, right? And it's a string. Then I'll call in my prompts. Let me add my return statements. All right. So this is the first portion of our code. Let's run it. Oh, hold on. Multiple definition of name. Oh, yeah. Because I have PID also here. So it's actually adding PID to it. So let me move MKDIR, then T. So you can actually prefer to do like input multiple commands at the same time. So I want to create this folder whilst I will move the PID into our test folder, right? And I've already created the directory, right? So, okay. So let me just move PID. Let's go to this. Oh, I'm in GCC. Let's see. Run. Let's see. Our shell, it's actually working. We've been able to print something out on the screen. And once you are getting this output, you are doing it right there. Now let's move back to our main header file again. Main.c, right? Yeah. Now, once you are done, there should be a way where we'll need to implement how we will need to accept an input from the user. Because we know that when you print something on the screen, the next thing that the shell does is that it's just waiting to accept an input from the user. So it is now time for us to inculcate the getLine function. All right? To inculcate the getLine function. So we will call our getLine. So say getLine. And some parameters that getLine will accept, but getLine accepts the addresses of those parameters. Yeah, someone. Yeah, is there a question, please?
Like
add E.
your get line
Get
is
line.
not complete.
Yeah. And you just underlined. Chairman, I didn't see anything. Okay, so now we just want to say, okay, let me just add buffer instead. All right. So, all right. I think this will be better. Then maybe this one too. Say size, right? Then the last parameter, whilst we're doing the whiteboarding, what did I say the last parameter will be in our case? What should it be? Yes. So you're going to accept our input from our keyboard. So it's going to be the standard input. Now, we want to verify that actually our get line is working. So we need to print our buffer out. All right. So we just have to call printf, then our string format specifier, then our buffer. Now, see something. Here, I added a new line character, but for this printf, I didn't add a new line character. Who can tell us why I did that?
Okay.
Repeat your question, please.
Yeah, I'm saying that for the line 17, this printf, I added a new line character, but on line 14, I didn't add a new line character. So why did I do that?
Would the prompt
And then because
Yeah, who is talking?
Okay, in a normal shell programming, when you give your command, the shell go to the next line to print the output. So yeah, I think that's my answer.
All right, cool. All right, wonderful. All right, so I think Abdul asked a question whether you need to use the scanf. Please, no. So as we're dealing with the whiteboard, then I actually explained why you have to use the get line. And actually the recommended or the requirement is that you're supposed to use the get line function. The reason is because scanf does not grant you most of the privileges as you prefer. You see that get line specifies where you will need to accept the input from. All right. For scanf, it doesn't wait for you to input, let me say, anything, any other thing at all. It will just it will just accept it. But get line actually uses malloc. All right. It's dynamically allocate that for you. Then it also calculates the size of of those entire string. Then it will also specify where it is accepting the input from. All right. And get line also, I think it returns a particular number. Let me see. Yes. So get line also prints out or possibly returns the number of characters in the buffer. All right. Of which for scanf, you'll not get all these privileges. All right. Yeah. So that's the reason that they are recommending that you should use the get line. So get line actually give you this privilege and it reduces your stress. Okay. So that is it. So as you can see, I think Life already explained that and he clarified that question for us. That's because on that same line, we want to tell the user that just input your command on this same line. And we are waiting for you to enter it before we do any other thing. So we don't need to actually drop our cursor to the next line, right? That's why we didn't introduce the new line character. All right, so now let's just exit from our program. I think there is something that I missed. Yes. There's something I've missed. So our buffer, I didn't initialize it. Our size to the same thing. All right. So buffer is actually a character pointer. All right. So we can actually initialize it out here. All right. So here's buffer. And we are saying that, okay, character pointer. Yeah, I almost forgot that. And our size is going to be of the type size T. And get line is of the size S size T. So S size, right? Let's assign size to it. Yeah. So let me just say it's equal to 0. Cool. Then we are good to go. Oh, and lest I forget, I already said that buffer is being allocated a space dynamically by getLine. So let I don't want to get into trouble. Let me free because I don't want to get a memory leak. So let me free my
Yes, I
buffer.
remember you said we must always free when
Yeah.
we done. We wrote
So I
three,
don't.
not free.
Oh. Yeah, thank you. Okay. So free buffer getLine. Okay. Um I believe you are good to go. Is that true? Yeah. So for size, it is size T, but not SS size T. It's getLine that is of the type SS size T. But size is actually of size T. This I hope is clear. All right.
No clear. Please explain again. Which one is size? S size T and
You say?
what you just
Okay,
explained now is not clear. Which one is S size T?
so let's go to the man page. getLine. So getLine is of the size S size T, right? And size, this one, is of the size T, as I've just initialized it with it out there. All right. Yeah. So getLine its own is just a function. It's a function and it's returning the type SS, and that's S size T, right? All right. So this is yeah, I forgot to add my header file in my library in my header file. So let's go there and let me include it. All right, cool. Now see, our shell is waiting for us to enter something. So if I say hello, now see, it's printed it out on the screen for us. Hello, and it's exited. Cool, wonderful. Now let's see another thing. Let me enter hello world. Now it's printed hello world for us and it's worked. Wonderful. So that means that we are moving forward, we are progressing, all right? But we've not gotten where it's working perfectly well as a shell should. But from the beginning, it's cool. It's okay. So let's go back to our main.c file and let's implement our loop. All right. We just want to implement a while loop. And with a while loop, we'll be able to what? To so we just say while one, all right? So we all know what while one means. That means that whilst true, or possibly whilst our condition is true. So whatever that it is. So we want to actually return. That's okay. Yeah, that's all. That's all. That's all. We don't need any other thing again. So that's all. Now let's save it and let's exit GCC. And it's compiled fine. Hello. Now it's printed hello, and it's waiting for us to input another thing again. And I'll say hello world. Wow. Still printed it out. And another prompt popped up again. Okay. Hey. This is wonderful. Now, see, it printed it out. It is still waiting. So now, how do we exit? If we type exit, aborted, free double detected in what? T cache, whatever. Okay. So you see that now. Okay, all right. So actually, where I place my free is its rate is giving us a problem. So I'll need to actually cast it out somewhere for it to work better. All right. So let me go back to my main. Let me try and drop free. After our while loop. Right. Now let's save our code, GCC. Compile it. I'll say hello world. New 1, new 2. Okay. Exit. Find A. That means that if we enter any other thing, it's just giving us the same feedback, but we cannot exit actually. The only thing that we can do to exit from here is Control C. And we know that actually Control C is just like a hard code shortcut to close a program. All right. But in the recommendation or in the requirement, you're supposed to implement the Control D. And Control D is actually the shortcut that return an exit status to a running program. All right. So it actually allows you to close from that particular program. So you're just going to implement that exit status right now. So open our main.c file. And it's our buffer. All right. So after get line, remember that get line is receiving an input from the user. All right. That's the keyboard. So everything that you enter on the keyboard, get line will read it. So if that is so, get line is required to return some number of characters. But remember, they already said that get line will return the number of characters in the buffer. And this actually the size of those total characters. And this, the buffer, or let me say, the variable that is actually hosting or holding that entire string. So if that is so, then I want to implement num underscore cars. That means that number of characters. But I'll need to declare, or possibly, I'll need to declare this particular variable. I remember I also said that get line retains s size t as a data type. So if that is so, I'll need to initialize our num car by s size t. Okay. All right. So let me add s instead of. All right. So now, how then will we be able to pass in our, let me say, our Control D command? All right. So Control D, we know that if you want to exit from a program, you have to call your return into brackets -1 your program will close, right? Yeah. So that is it that we are going to implement here. So get line, if you enter the control D command, it will actually return -1. That means that any cars will return -1 if the shortcut that we inputted on our keyboard is control D, right? So we just raise a condition that if num r's, all right, is equal to -1, then we would like to, first of all, print something. I'll say that exiting, all right? So it's exiting. Sure. Yeah. Add our new line character. And we'll return -1. This will close or possibly terminate our shell. So please, do you understand, or is becoming too much complicated? Can we box on? Cool. All right. Yeah. Thank you, Seth. Okay. So now we'll just have to save our file, recompile our source code. Now, if we execute our code, we say hello world. It is working. New 2. It's also working. Okay, let me add a name. It's also working. But the moment that I hold Control B, see, it's type exiting shell, and it's exited from the shell. All right, cool. So Control then B, it's exited. But if I type exit, it's still not working. So at the long run, there will be a particular aspect where we'll implement this exit so that if we pass exit to our shell, it will actually do what? It will actually exit. Like, seriously, exit. Okay, so Control D. Control D. All right. Okay, so let's go back to our main.c file. Now, I think, okay, so we have 30 minutes more. All right. Did we highlight tokenization? Yeah. I highlighted tokenization during the whiteboarding. So we're actually going to implement tokenization, all right? So if we let's go to our man page. So we talked of string talk, right, which is a command for tokenizing strings. So we say it's used to extract tokens from strings, and it comes from the string.h library. And string talk returns a character pointer, all right? And it accepts a character pointer, which is actually a string, right? Then the next one is actually a character pointer, which is actually a delimiter. Okay, right. So if we read downwards, we can see that string talk function breaks a string into a sequence of 0 or more non-empty tokens. So every token needs not to be empty. All right. Okay, until it gets to the last token. So on the first call to string talk, the string to be passed should be specified in string, which is str. In each subsequent call, that should pass the same string. Str must be null, right? So they are saying that in each subsequent call of our token, our str, instead of just passing str, we should pass null in our string talk. So that means that we will need to implement a loop a second time for string talk. Then we'll be assigning the null terminator to our tokens, like we are splitting them separately. All right, automatically string talk will just detect those words, or let me say those tokens, and will assign them to the variable. All right. So we also have the delimiter. So delim arguments specify a set of bytes that delimit the tokens in the parsed string. The caller may specify different strings in delim in successive calls that parse the same string. All right. So each call to string talk returns a pointer to a null terminated string containing the next token. Right. So I think that's it. Okay. So let's go to our main and let's implement our token here, or possible tokenization. So with the implementation, any question? So let's box on.
There's a question in the thread, Manu.
Right, thank you. Yes, yes. So you can actually decide to use that EOF. Yeah, you can actually decide to use EOF. Yeah. Okay, so okay. All right. So the next thing that we're going to do is that we want to implement tokenize strings. And you see that when we tokenize our strings and we actually decide to print them out, you see that they are actually being split into separate proportions. But before tokenizing our buffer, which we have, we want to actually create, or we prefer to create a duplicate, right, of the buffer. We want to actually create a duplicate of the buffer. So let's implement another variable, or possibly another pointer. So we just say buffer, possibly here. Let me start with CPY underscore buff. All right, yeah, that means that's a duplicate of the buffer. Then we'll implement, we'll need to, let's allocate a dynamic memory allocator for it, because currently here we are calculating for the number of characters. So you can actually use this to allocate a space for this. Because remember, buffer is automatically being given, or possibly is being assigned a space. So we need not to worry about that. Okay, so now we'll just say CPY have equal to malloc. Then we'll call our size of R characters. Then we'll call num R's bytes, and cool. But after every memory allocation, we need to make sure that we need to raise a condition whether it worked or it didn't work. So CPY If it is equal to null, we want to say, okay, print f memory allocation field, right? Then I'll exit with a -1. Oh, okay. Let me use the p error so that it will output it to the standard error. All right. Yeah. This will happen only when there is an error. Okay. Then it will exit from our program. All right. Yeah. So the p error actually works just like any print function. All right. Yeah. Just like you can actually use the write function to print to the standard output, or possibly to print to the standard error. Right. We know that we have so many let me see, macros, all right, predefined in C. We have the standard output, we have the standard input, we have the standard error, and all that. Okay, so P error actually grants us a privilege to print to the standard error. So let's just use the man page, because that's what we need to use all the time. So P error. And we even have FS print, we have F print, and all that out there. So it says display MySQL what error message information. Don't worry about this. Okay, don't worry about this. So displays the error message. So we use P error to display error messages. All right. Or operating system error codes. Do you understand that? Cool. So P error attempts to be flexible in understanding its argument. For example, for the value this, then that's error. Man, massa, this is too much. Okay, so don't worry about that. So P error, we just use it to print an error message on the screen. And the reason is because it only happens, or possibly it will only print out only when there is an error. Because if you use print or any other print function, most of the times, unexpectedly, if the condition is true, right, it will actually print it out. Meanwhile, maybe it might happen that it wasn't an error. Okay, yeah. So just to prevent you from having an unexpected output in your code, it's preferred that if it is an error, print an error. If you want to really print an output which the user really want to see, they should actually print it as what? An output. Just like we use the prompt and we use the printf to print the prompt. All right. If it's an error, just use print error. That's P error, sorry. We also have so many variations of what? Of prints. I think, yeah, let me see whether the others are here. Okay, don't worry. We have F print and all that. Yeah. So you see that we have print F, we have F print, we have D print F, S print F, S, and all these things. They are all here. So when you read through all the documentation, you know how to use them and at what particular time that you need to use them. Yeah. Currently, we still have the privilege to use P error in our code. It's part of the requirement. So you can decide to use printf, but printf in some cases might give you an unexpected output, right? If you use P error, it happens only when there is an error. This set, I believe, is answered, right? Plus F. Okay. So now we've allocated our memory. Okay. So the next thing that we're going to do is that, yeah, as already said, we want to implement the string copy. All right. Okay. We want to actually create a duplicate of our buffer. So we're actually going to use string copy. Okay. Most people would prefer to use string dump, but string dump, I've not actually used string dump before, but some string dump also have certain side effects. I don't know who is an expert in string dump here. Maybe you can give us a justification in that, because I don't usually use that. I think there are some advantages in using string dump. Is it string dump or string dump, whatever? Okay, so strc UI, yeah, string copy. Then our destination is going to be yeah, I use CPY buff. Yeah. Yeah. So I use CPY buff. Then our source will be buffer. Okay. So we all know how string copy works. We are just copying the contents of this and we are pasting it inside this. Yeah, that's all. That's all about that. So, I believe that's it. Okay. Chairman. Okay. Sorry about that. Okay, set. Yeah. I see that you are typing something. Oh, okay. Yeah, so actually, yeah, I think set. Okay, so all right. Okay, so yeah, let me make a justification. So if you read the documentation, there are some required commands that you can actually use there, right? And you have the privilege to use anything at all that you prefer. I think for the simple shell projects, you have so many functions that you can actually implement, right? Yeah. So you can actually use string copy in your code. Don't worry. Yeah. So actually, it's actually there. You can see that's also there. You can use, if you prefer, you can also use string down in a way. But you, along the line, it might happen that there will be no need for you to use string copy. All right. You don't need to force yourself to go and use string copy. If you prefer to go by the buffer alone, but this is just for us to keep track of our main, let me say, our main text. All right. So it doesn't, we don't lose it along the line or anything like that. Yeah. So we just want to use string copy to deal with the contents of it out there. It's a beg, but you have the privileges, but it's still limited. It's not everything that you can actually use. Right? Yeah. So it's just that you have to read the documentation, or let me say the requirements very, very well, so that you know what is being expected of you, so that you don't get you don't put yourself into trouble. So now, once you've copied this, let's see the next thing that we can do. Okay, now let's try and implement our tokenization here, right? So we've copied this. Let's try and implement our token. So, okay, I haven't created a token file, right? I haven't created a token file. Let me push this in here. Okay, so all right. So there are certain libraries that I still need to include in our header file. But once I'm done, I'll just go back and include them in there. But string talk is already being found in string.h. So even with that, there'll be no need for me to use it out there. So I'll need to add string talk to also here. So I'll just call my token, but I'll make it a pointer, right? It should be a character pointer because it will be storing a string. If you tokenize your string, it's just separating those individual words using the delimiter. Now let's try and specify our delimiter also here. And it's actually going to be a constant character. All right. And I'll name it delim. Right. Yeah. We just name it delim. And we just specify a new line character. They say that we've passed 2 parameters to it. So when it encounters the space, right, it will break the first word and it will assign it to the token. All right. So don't worry, along the line we'll get it. Then it will assign it to the argument, like a particular variable. Right? Then if it gets to the next word, after the next word, there is a space. So it's using the space and the new line character it's using them as the delimiter, right? So when it encounters the new line character, it knows that it's actually at the end of what? Of the let me see, the string, right? Okay. So we are done implementing delim. We've declared token also here. So now let's call in into brackets. Token is equal to CRTOK, which is string talk. Then string talk will actually accept 2 parameters, as you already know. But the first one will actually pass in our original buffer, which is this one. All right. So this will actually assign the entire buffer to it. Then it will also allocate the delimiter to it. So when we read the string talk, or when we read the man page or the documentation on the string token, is that when you pass in the string token, it will actually initialize the first token, right, to the variable. Okay. So you just want to actually see. And the next thing, let's just try and raise our condition. So raise our while loop here. I want to see if the token that we passed, if it is not null, that means that our buffer should definitely contain something. That's the reason that I want to actually assign it to our token, meaning that the first argument shouldn't be empty. So we just want to say that if token is not what, then what do we want to do? We want to actually do what? Increase the number of what? Of our tokens. But I record I have not declared this one too, right? Yeah. And I didn't even add a semicolon. So int num, let's call int equal to 0. I think this should be fine. Yeah, okay, that's it. Okay. So we are just saying that as long as the token is not null, all right, we just want to count through the tokens. That means that we want to know the number of tokens. Remember that we should also be able to return the number of words that the user or the number of argument that the user passed. We're actually going to use it to allocate a memory, all right, or possibly dynamic memory to our individual variables. Okay, we'll get there. And once we are done, we'll just call token again, and we'll just say token and string talk, right? And remember, when we read on the documentation, they said that on a subsequent call of the string talk, we should pass in null and the delimiter, right? To pass in null and the delimiter, so that we want to increment the number of tokens again. So this includes the what? The new line character, or possibly the null terminator. All right. Okay. This is also part of the tokens. Now, what is the next thing that? Okay. Is there any question? Yeah, exactly. So DAM creates a duplicate, but DAM actually allocates a memory for the destination variable, all right? Or possibly that particular duplicate. It dynamically allocates a memory for it. Yeah, that's it about dump. But I don't know much about string dump. Yeah. Now, if you prefer, you can also use that. There's no harm in try and error. Okay, so number of tokens. And after that, we now want to introduce argument vectors and argument counts, right? Yeah, argument vectors and argument count. Because one thing is, for example, just like entering the move command. Okay, so if you enter MV, you must point to the source and the destination where you want to move your file from. And where you want. To paste it. So it's the number of tokens that the user like. We want to actually print all those tokens out on the screen so that we see that they're actually working. So we just initialize our adv, but let me pass them here. So done. What is happening? Okay. Yeah. So in C, all right, then we know that or argv is supposed to be a character double pointer, right? Yeah, that's cool. So now at V, we'll need to allocate dynamic memory allocation for it. Let me clear this. We'll pass in car. It's going to be a character pointer. We'll multiply it by the number of tokens. But not, yeah. So the string length, sure. Let me close my last braces. Hold on. The number of tokens. Yeah. So this will be the number of tokens instead of the string length. So num underscore tokens. Yeah. So a V is actually what? A double pointer. And we are actually initializing or possibly multiplying the size of a character, and we are multiplying by the number of tokens. Okay. And whatever size that we'll get, we'll allocate it to add fee. Now, after that, we want to create or possibly tokenize our new arguments. That's our new duplicates, which is the CPY buff. We want to tokenize that one, right? Then we use it for the rest of the implementation. So we'll call string talk, then CPY buff, then the delimiter. Okay. Once you are done, we raise our for loop. We say I is equal to 0, right? I believe you all know how the loop works. We'll say that as long as token is not equal to, so long as it's not equal to, so as long as we've not gotten to the end of what? Of our line, or possibly, let me decide to pass in null, right? Then I'll just say I plus plus. And for this first parameter that will pass in here, we'll call add v with index I. Oh, it's 12 a.m. Yeah. So it says after this, I think we'll be yeah. And for the night. Hello, can you guys hear me? All right, all right. Yeah, okay. I thought my network jumped. Okay. So,
Well, I
well,
think your screen is off.
all right. So for this, I see. So screen now. Okay. All right. Yeah. Yeah. Okay. Okay. So now we'll calculate for the string length of what of our token. All right. And remember that when if this then happens, it just tokenize or possibly just assign. Okay, yeah, I think my screen have stopped sharing again. Let me reshare. All right. So yeah. So I fixed it finally. Okay. All right. So as I was saying earlier, if you run this string doc command, as you read from the documentation, you got to know that the first call of this command will assign the first token to the what is subsequent variable. So token is now holding the what the initial okay, so our variable token is now holding the initial or the first token. All right. Yeah. So we are saying that so long as token is not equal to null, right? So long as it's not equal to null, then we want to go on and assign the subsequent tokens to our argument vector. All right. Cool. So that's what this means along. Now, after that, we want to actually inculcate string copy, right? Um, let me try and look at something. Okay, so let's inculcate string copy again because see, we are passing token. We are saying that so long as it's not equal to null, right? And with each and every individual count, we want to move to the next what token, right? So we will need to hit strcpy, yeah. Then we'll pass in our adv, right? And token. You see that now token is hosting the initial argument of our entire string or the initial token of our entire string. So we've allocated a location, that's a memory location for it. Once you're done, we just want to what to assign token to our adv. So with each and every single count, we want to just assign token to it. So you see that at v0, will be the name of our command in case if we want to look through the path, we'll pass adv0, right, to our exec fee and its subsequent path, and it will look through the path to see if that particular program is there. If it is not, it will return command not found. Okay. All right. Now let me inculcate a printf function here, and let's see if it is actually working for us. So %s, then a new line character, then I'll just pass agv with the index I, and let's hope that it's working. But remember, we are still dynamically allocating some stories or some spaces for most of our variables, right? So free agv, right? Then which one again? CPY buff. Yeah. Right. So let's exit GCC. Okay. Oh, I've forgotten so many things. Implicit declaration for string length. Okay. str talk. Okay. Yeah. So there's an implicit declaration for that. See, I mentioned string.h and I forgot to even add it in our header file. But I already included that. All right. Good. Line 53 comment. So 5-3. Yeah, I didn't add my last braces. So that's what affected all the rest. Yeah, I didn't also initialize. I didn't also, I didn't also initialize the I. So I should be here. So int I, a comma, right? So that's it. Okay, so let me recompile. Now it worked. Let's run our source code. Okay, shell hello. Run into an infinite loop. Yeah, because of the while loop. Because of the while loop. So let me go back. Let's see. That's the for loop. Sorry. The for loop. So whilst token is not equal to null.
Sorry, in the main argument, I think you put the integer C, probably it can be used. I'm just saying.
Yeah, yes. For C, C will use it along the line. But since we are using argument vector, I cannot ignore the two of them. So let me just typecast it because actually if I was to be using let me say those error checkers, that's the WO and all that, I'll be getting flag for that. So let me typecast it to void for now, since we are not using this C. All right. Okay. Yeah. So I think for this last one, yeah, there's something that I left out. I believe so. Yeah. So I get it now. I forgot to retokenize, like to recall the token again. We know that there is a first call of our token and subsequent call of the token. We need to pass string talk, right? Then we need to pass in null and the delimiter, right? That's basically the reason we're getting that error. So let me recompile. No, recompile. And let me say hello. Hey, you see that it printed out perfectly fine. The reason we are getting this multiple output is because we have multiple printfs in our code. If you go back and we comment this one out, the last printf is buffer, right? That's the reason we are getting two print out. So we can decide to comment it out. So let's recompile again. Let's rerun our code. I will say hello world. I didn't spell my world right. See, we're able to get hello, then this thing, which is whether world or whatever. So hello set, for example. Also being able to say hello set. So you see that our entire string have been what? Tokenized. It has been split into separate sections. So I can say hello, good morning. I think it's morning, right? How are you guys? I add my comma. So you see that it has tokenized every single one of them. And it's actually using the delimiter, which is actually the space between them. All right. And it's automatically can notice that this is the end of the string by what? By encountering the null terminator. All right. And you see that we are able to print all these things out. So, Seth, I think we are done. We've consumed so much time today, almost about 3 hours, right? Yeah. So we've talked about PIDs, we've talked about how to implement the shell in these various ways. Maybe the next time that we meet again, we'll talk about how to actually implement the execv, where you can actually use the path, where you can actually implement your own built-in commands and any other utilities that we can actually implement. All right. Okay. Any question, please, for this? As simple as our simple shell works. So you see that actually this is a simple program. It's not working perfectly as a shell should do, but it's still giving us a satisfaction, right? Because it's giving us a prompt. When we input something, it breaks or possibly tokenizes our inputs. So just like the world, it tokenizes our inputs and it breaks each and every one of them down. So let me try and implement, in case if there is multiple space, let's see something. So I cannot move through my characters. That's wonderful. So it still tokenizes them. Even if there is a double space, it still breaks it off where it doesn't, let me say, add up that additional space to it. So it won't give us any error. Cool. All right. So, set. We are done. for for today and yesterday night. Yeah. Yeah. Yeah, it's cool. It's cool. It's cool. All right. Okay then. So tomorrow, right? Okay. All right.
Yeah, sorry, Emmanuel, before you go, can you copy the code for us? Probably you might just want to modify it
Yeah,
on
I'll
our end.
yes. Yes, I'll paste it in the thread. Actually, I'll not copy it. I'll send the file to the thread so that you can just look through it. Yeah. So actually, I'm just trying to add them up right now. I'm just trying to push the file right now so that you just have a look at them. Yeah, you're welcome.
Thanks, Seth.